Hello everyone. In this session, I'm going to talk about the regression trees. So regression trees are similar to another kind of decision trees. Just like a classification tree, they are also another kind of decision trees. But here, the response variable that we are trying to predict, that we are trying to model is a numerical variable. If you remember, in the classification trees that we have performed, the response variable was primarily a categorical variable. So in some cases there could be more than two categories, or in some cases there could be exactly two categories, which is a kind of a binary kind of a variable. But whatever it is, the response variable is a categorical variable in a classification tree, whereas in case of regression trees, the response variable is primarily a numerical variable. So I may be interested in modeling the prices, or I may be interested in modeling the sales, right? So when I'm trying to look at modeling any of these elements, which are primarily numeric in nature, I can take the help of regression trees. So in this session, I'm going to look at four different types of regression trees. Though the initial basic preliminary regression tree is something that we are going to initially look at. So just like a preliminary classification tree that we have used using the tree package, I'll be using a similar kind of thing in case of regression tree. Similarly, we have a conditional inference regression tree. We also had a conditional inference classification tree also. So now we are using conditional inference regression tree. Similarly, we are talking about evolutionary regression tree, right? We had evolutionary classification tree, whereas now we are using evolutionary regression tree, and we are also having linear model based recursive partitioning, which is more like your logistic based recursive partitioning model in case of classification. So we are using that for our regression model as well. So these are the four different kinds of trees that I'm going to look at. In this context, the data that I'm considering is a simple insurance related data which is stored in this particular folder of my system. So I'm loading that and saving it into a variable called insurance. I'm doing a quick summary of this particular data set by using summary of insurance. So I could see that, so this is what is my objective here. I have a variable called insurance charges, right? And it is looking more like a numerical variable. I see that it is ranging from a minimum of 1122 to a maximum of 63,000. So that's the kind of values that the charges is typically carrying. So I want to take this as my response variable, and all others I want to take as my predictor variables or explanatory variables, the age of the person. So I want to really assess whether the insurance charges that the person needs to pay are dependent on the age of the person, which is having a minimum value of 18 to a maximum value of 64. The sex of the person, so females and males looks like more or less uniformly distributed in the data. The BMIs ranging as low as 16 to as high as 53. So is there any relationship between the insurance charges and the BMI of the person? Then the number of children, because this is a kind of a comprehensive health coverage for the entire family. So is the number of children playing a role 0 to 5? So is it playing any kind of a role in terms of determining the charges? The smoker status of the person, we have 1000 odd people who are not smokers, whereas 274 people in the data set are smokers. And region wise, we see that there are people in from 4 different regions: northeast, northwest, southeast, southwest, and probably the proportions are more or less uniform. Now this is what is the story which is there in front of us. Using this, I want to build these 4 trees and see to which one of these is typically giving a good advantage in terms of modeling the charges by considering all the remaining variables as the predictors for the insurance charges. So initially, let's get started with a preliminary regression tree. So this could be installed from the tree package with the tree function, just like the one we have used for preliminary classification tree. That's the same thing I'm going to use here as well, right? So I would like to use the tree package with the tree function. So I think it's already installed on my system, but if it is not installed, it's better that I install it. Because it's already installed, I'm simply loading the tree package, library tree. So the tree package is typically load, and the tree function, right? If you want a quick reference, you can very well put a question mark tree to understand what the tree function typically is containing. But now, typically the most important thing that I have to give to it, Z, which is the data frame. Here it should contain the continuous response variable. So for Z, in this case, I would be giving the field called charges, because that's a continuous variable. The data is a data set of attributes that is used to build the tree. So I'll use a dot saying all the other remaining columns attributes would be used to build the tree. Split. Here there are 2 types of split, as we have discussed earlier also. I can use deviance or a Gini coefficient as the splitting criteria. So I can very well do that kind of, so I can try one model with deviance, I can try the second model with Gini coefficient, and see whichever model is doing a good job in terms of estimation. Now, if I have to assess what is a good model, in case of classification, what did we do? We have taken the training data and the testing data. We have built the model on the training data. We have tested it on the testing data. And we have looked at the accuracy percentage. How many of the values are correctly classified versus how many of them are wrongly classified, which has given me the error rate of the model. Here, we don't look at it that way. We will typically look at it from the perspective of the continuous variable. It's not a categorical variable, it's a continuous variable. So when I'm comparing the actual test data versus the predicted data, I would look at, I cannot look at the accuracy of the model in terms of the accurate classification, because it's not groups, it's a number. So we will be using some other mechanisms like R squared or mean squared error, some such kind of error computation mechanisms to assess what is the goodness of each of these models, right? So let's get started with one example which will simplify the process for us. Load the tree package. Yes, we have loaded it. Get the data. We have done that. So this step is over. I've loaded the tree package. I've got the data for which the regression tree need to be built. So initial inspection of the data, the summary has been performed. I don't see any kind of NA values in the data. If there are NAs, it should be, I should have some kind of a mechanism to handle the NAs. Either I omit all the NAs or probably replace the NAs with the mean value or some such kind of stuff. I should be able to do them. Some kind of imputation I need to perform on the NA values, because if NAs are there, the model cannot be done, model cannot be executed. So I have to take enough steps, enough care to make sure that the model can be executed without any kind of a problem. Then the next step for me is split the data into a training data and the testing data. Yes, now that's the part for me. Let me consider how many rows are there for the data. So I'll take n row of insurance. Right, I'm taking n row insurance. There are 1338 rows. Let me take the 70% of this. So which is saying 936. So approximately 936 of them will go as a part of the training data. 937. 937 will go as a part of my training data. Remaining 401 will go as a part of my testing data. So I'll take a variable. So let me set a seed value. Set.seed 1000. Right. Now I am taking a train. The train now is taken from the sample function, where from 1001 to 1338 I want 937 values to be randomly selected without any kind of duplication. So I am setting replace equal to false. So this is what is my train using the sample function. Based on that, I can very well compute my training data, which is a subset of insurance, where I am considering the rows that are there as a part of the train and all the columns. And test data for me is a subset of insurance again, where the rows that would be included is those that are not there as a part of the train, but all the columns will be included. So based on this, I got my training data and the testing data. Now this is where I can go ahead in terms of fitting the decision tree using the training sample. So I can very well fit. So let me call fit tree. Right, fit tree, and let me call it as the deviance. I'll use deviance as a splitting criteria out here. So here tree. So here there is one more advantage. If I want to take it on the data as it is, the charges as it is, I can very well do the regression model based on charges. But if I want to transform these charges in some way or the other, let's say logarithm and all, I can even do that kind of an aspect as well. So initially, let me just do it with the original itself. So let me call charges tilde dot. So this is what is my formula, and in this case I am taking the data as my train data, and of course the split criteria that we are using is the deviance. Deviance is the splitting criteria that we are using. So this way, let me build 4 models. Then the next one is Gini. I want to fit that Gini as well. The only difference being this. Now I want to look with logarithm as well. Instead of directly taking the charges, I will take log of charges just to see if the model is anywhere better. So instead of taking the charges, I'll take the log of charges, and probably let me call this as fit tree log underscore deviance. Right? And the same one, I can very well do the Gini as well. So I have 4 models in front of me. I want to try out all the 4 models in this case to see which one is doing a better fitment of the data. Probably you can try some other transformations as well on the data. So this is what initially I want to try, right? So let me first type in the name of the model, fit tree deviance. So this is the tree at this moment, right? You could see here the splitting criteria is, first thing is smoker equal to no. versus smoker equal to S. This is what is the initial splitting criteria. N, there are 739 records which are there with a smoking criteria no and 198 with a smoking criteria S. And this is the deviation that is there as a part of this group. This is the deviation as a part of this group. The Y value is being projected as 8517 out here, whereas for people who are smokers, the charges are coming out to 31,930. And there are 4 terminal nodes. So the whole model is based on the smoker status, the age, and the BMI of the person. The remaining things, the gender, the number of children for the person, as well as the region to which the person belongs to, they are not playing any kind of an important role in the determination of the insurance charges for the person. Similarly, when I am going with the Gini coefficient, what is the model that has come out? Oh, Gini coefficient is not able to do anything better than original. So it's there are no branches in it, which means it is saying the model is completely random. So I don't have any kind of a model in case of Gini coefficient. Probably if I am going with the log deviance kind of a model, which means I am taking the log charges rather than the charges originally. In this case, things are much better. Initially, smoker equal to no versus smoker equal to S. But within that, again, age is being considered less than 32.5 versus greater than 32.5. And within that, again, children less than 0.5. So, which is like 0 children versus children greater than 0.5. Age, again, another bifurcation of the age less than 22.5 versus greater than 22.5. And in case of smokers, a BMI less than 30 versus greater than 30. So we have different kinds of nodes that have come out. So many terminal nodes that have come up in case of the preliminary regression tree when we are taking log of charges. But again, log of charges using the Gini as the splitting criteria, wow. It's a big model that has come out using the logarithm and using the Gini as the fitting criteria. Probably there should be a lot of overfitting for this model because there's a big branching that has typically come out. It looks like as if it's a kind of a personalized model for each person, which may or may not be a kind of a good solution for us at all. So that's how I can very well look at the details of the model by simply typing the name of the model. And at the same time, I can do a summary of all these 4 models, right? So I can very well go with log Gini. So the summary wise, it has said that the residual mean deviance is around 1.1095. There are 145 terminal nodes. It's a big, probably there is a kind of big error that is possible when we are testing it out on the testing data. We will try and look at it. But at the same time, if I look at the deviance out here, okay, the minimum is minus 1.02 to a maximum of 2.42. The residual mean deviance is slightly on the higher side, but there are only 7 terminal nodes. Not all of them are typically used for the purpose. Whereas here only 4 different variables have been used to build this tree. And now if I am also looking at a simple deviance kind of a model, in this case, yes, I could see that the residual mean deviance is around 22.72 million, but there are only 4 nodes in the whole process. And the whole tree has been built using the smoker status, age, and the BMI of the person. Whereas the last one, when I'm going with the Gini, it looks like there's only one terminal node. So none of the variables are typically influencing. And you could see that the typical residual mean deviance is too high. 149 million is the residual mean deviance. So these are the four kinds of models that we have come across when we are typing the summary part. Right, in the summary, now we could see that the terminal value at each node. Now if you look at the terminal value at each of the nodes, it is the estimated mean value of the response variable of all the observations that are falling into that particular node. So I have very much used the summary. So we have looked at the residual mean deviance. The lower it is, the better it is. The distribution of the residuals from minimum to maximum, mean, median, first quartile and third quartile are typically being displayed. I can very well do the plotting of the tree using the plot function. So I can very well go with plot of fit tree deviance, and on the top of it I can very well do a text of the fit tree deviance. So this is what is the tree: smoker status, age less than 42.5. There are, I could see that the insurance charges are around 5,500. For people whose age is more than 42.5, the insurance charges are typically around 12,340. Whereas for people who are smokers, I could see that if their BMI is less than 30.01, I could see that their insurance charge on an average is around 21,000. But if their BMI is on the higher side, the insurance charge is shooting up to 41,390. So that's the way I can even try out for the log as well. Right, I don't need to try all of them. I'll just try two of them. Rest all you can very well go ahead. In case of log, right, so I think I need to do the log here as well. So this is how the log tree is working. Smoker, age less than 32.5, but within that we are looking for children less than 0.5 versus children greater than 0.5. So I could see that slightly with the children, the insurance charges are slightly going up. Even with age, the insurance charges are slightly going up. But for people who are smokers, it's only the BMI that is mattering a lot. And I could see that the BMI, as the BMI is increasing, the logarithm of the insurance charges is also very much increasing. So that's one way we have gone across with the model. Then we could also see whether there is a possibility of overfitting in the data. That is what we have seen in case of classification tree also. So I can very well go with a leave one out kind of a cross validation in the whole process, right? So cross validation is something that I can very well go with. So I want to test out how many values I can go with a CV.tree kind of a model. CV.tree we have used in case of classification also. So I will look at the same CV.tree with respect to the deviance as well as the log deviance. So we are using a leave one out kind of a classification. Cross validation models is what we are using. So I will look at it as cross validation underscore, I'll call it as fit tree deviance. Cross validation underscore fit tree deviance is the name of the model that I'm using, where I would be using cv.tree as a function, and I would be considering fit tree deviance as the model, and I will be setting the k value which is equivalent to the overall size. So I will play around how many values should be included as a part of the testing data. So I could very well say 401. And based on that, I have got a CV underscore fit underscore deviance. The same way I will go with CV underscore fit underscore log deviance. Right. I will also use fit underscore tree underscore CV underscore fit underscore tree underscore log deviance. Here also let me take it as log deviance. So I have got another tree, And similarly, if I want, I can do it with respect to Gini as well. Now, if I look at this tree, I could see that, yeah, for sizes 4, 3, 2, 1, these are the typical errors that are cropping up. So I could see where the error is typically minimum. And similarly, when I'm going with log deviance also, I could see where is that the error is typically higher. So I could very well go with the plotting of these two things. So let me go with simple deviance for the plot. So this is where it is showing that when the tree size is approximately 4, this is where the deviance is looking much lesser. So there is no need of pruning the tree in this case at all. But when I look at log deviance, what is happening? When I look at the log deviance also, it's the same story that is coming up. When the size of the tree is approximately 7, which is what is the current scenario, that is when I'm getting my deviance to be the minimum mode. So I could very well continue with the 7 being the size of the tree. I don't need any kind of a further pruning of the tree. So this is where I have done the validation using a leave one out. The plotted line has reached a minimum close to the number of branches in the original tree. So in this case, I really don't need to get into the pruning of the tree at all. Now it's time for me to typically go ahead with the testing process, right? I can very well say predict underscore fit tree deviance, right? So that's the predicted value that I'm going with. I'm simply saying predict as a function. The model that I'm using is predict fit underscore tree underscore deviance, and the new data that we are using in this case is test data. Test data is the new data for which we want to go ahead with the fitting part. So now the fitted values have typically come up. The same thing I want to do with log deviance. I'll go with a log underscore deviance. The model wise I'm using fit underscore tree underscore log underscore deviance, and I'm doing it on the testing data. So these are the two models that we are going with. So one thing is I can go ahead in terms of the plotting, right? Plot, I'll take the actual, which is the test data dollar charges. That's my actual values. And at the same time, I can also consider ped underscore fit underscore tree underscore deviant, that is the predicted values. So these two things I'll do a plot, and you see that so in the x-axis it's the actual values, y-axis it's the predicted values, and I'm doing the plotting of the same. So this is how the typical plot is coming out, and if required I can very well do the correlation between the two. Instead of plot, I will perform the correlation between the two, or probably I can consider the correlation squared, which is what we are calling as R squared. The higher the R squared, the better is the fitment of the model. So here I've got a correlation of 85.15%. Right, for this kind of model, when I have used the deviance as the splitting criteria and the charges as it is, I got the accuracy of the model to be around 85.15%. Whereas if I am doing the same thing with respect to the log deviance, right, I look at it as the logarithm of the test data charges. So here it is coming out to 83.39%. So when I am considering the logarithm, it looks like the values are not coming out to be that appropriate. Whereas when I am considering the reality, the actual values, I could see that the value, the correlation or the R squared is coming out to be 85.15%. So I could very well assess that the model which is using deviance as the base, and probably if I have to look at the Gini based log where there are 145 nodes that have come out, let's see to what extent that model is going to influence our analysis. So I'll take the log underscore Gini here, and even the predict I'm looking at log underscore Gini out here. And the correlation also I would consider correlation log test data charges, and even here instead of deviance I will take it as Gini squared. And this correlation also ended up with 83.27%. So overall it looked like the first one is much appropriate, right? So out of these models, right now whatever is the preliminary regression tree that we have considered, it appears that using the charges in the original form without any logarithmic transformation, considering all the other variables as the independent variables, building a tree with the training data and testing it on the testing data is giving me a 85% R squared on the testing data. So that would be the most preferred out of all the current models that we have. But at the same time, if I look at the other three models that I'm going to talk about in this session, if any of these models are going to give me a much better R squared, I would be typically preferring them over this preliminary regression tree model that we have created right now. Alright, so this is where we'll be moving on to our next set of model, which is the conditional inference reference tree model, and build it for the same data, try assessing how each of these models are differing and what is the kind of R squared each of these models is providing when I am doing the testing on the test data. But again, let me warn you again and again, there is no such thing called this model is the best. Right? There is no scenario where one model is always better than the second model. It's only that I have to test different models for a particular data set. Whichever model is giving me the high level of accuracy. In case of regression tree, the R squared on the testing data is one such kind of a measure of accuracy of the model. So whichever is one giving me that kind of higher accuracy would be considered for the prediction purposes in future. Alright. So with that as a base, let's move on to our next set of trees, for which we will be using the same example to proceed further. Alright. Once we are comfortable with the preliminary regression tree, we are moving on to the next important aspect, next model, conditional inference regression tree. So more or less similar to conditional inference classification tree. It's also a non-parametric regression tree, and there is a tree structured regression model that is embedded into it, just like a conditional inference classification tree. Apart from just building the tree, apart from simply breaking down the tree structure, there is an extra information that is provided at the leaf nodes level. That is what is the better assessment of the conditional inference regression tree. So this can be built with the party package using the C tree function, which we have used even for conditional inference classification tree also. So let me load the party package. Right. So here we have a function called C tree. Right. This is the same function which we have used even for classification tree as well. The only difference being here the Z is a continuous response variable. It's not a class. In the classification model, in the classification tree model, the Z was the column that is containing the categorical variable. Whereas in case of regression tree, Z needs to be a variable that is containing the continuous response variable. right? So the data frame associated with the response variable is what will be contained as a part of Z, and the data is the set of all the attributes which are used to build the tree. So coming to our example, the charges would be there as a part of Z, and the dot, which is all the other variables, all the other attributes that are used to build the tree, will go as a part of the data. Now if you see, these are all things that have been already taken care of because we are using the same data again. We have loaded the party package, we got the data for which the regression tree needs to be built, initial inspection is done, we have looked at if there are NA values. In this case we didn't have any kind of missing values as a part of the data. We have split the data into the training set as well as the testing set. We would be executing the model on the training set, right, and we would be testing it out on the testing data set. So we have to do the estimation of the model. So let me call it as fit underscore C tree, which is the conditional inference tree. I'll simply take fit underscore C tree, where I would be using the function called C tree. My variable, in this case, let me go only with the original. I'll not take the logarithm, right? So I'll take the charges, which is my response variable, tilde dot, which means I'm using all other variables as a part of my explanatory variables. The data in this case is the trained data, which is what is the training data that we have built, right? So this is on this is what we are actually building the C tree. So our C tree got built. Let's type in the name of the tree to get the details about this particular tree. Wow, this is the kind of a splitting that has come out. There's a lot of learning that has happened. 17 terminal nodes are there as a part of this tree. It has taken all these variables. The response variable is charges, whereas all the remaining 6 are being considered as a part of the inputs. Now you could see the way the tree got split. The smoker equal to S. That's one category. So we are talking about the smokers category out here, and we have smoker equal to no. So this is the first category that overall it came out, right? So probably it's the tree is looking like this. Of course we can plot the tree. So initially it is coming out as smoker. So this is the path for S, this is the path for no. Now within S again we are talking about a BMI less than 30 versus, so within this group we are talking of BMI less than 30, less than or equal to 30. So within this S category again we have a split wherein BMI less than or equal to 30 and BMI greater than 30. Now again within the BMI less than or equal to 30 we are talking of age less than or equal to 40 versus age greater than 40. So within this one more category, age less than or equal to 40, age greater than 40. These are the two categories that came out. Now again for age less than or equal to 40, we have got one more category, which is BMI less than or equal to 24.13 versus BMI greater than 24.13. Right, so this is how the tree got typically built. And again within this group of BMI less than or equal to 24.13, this is where I don't have any more. There are 19 elements and this is my leaf node. Whereas where BMI is greater than 24.13, again there is a split that has occurred. Age less than or equal to 27 versus age greater than 27. So that's how the whole tree is getting built, right? We can very well do the plotting of the tree, and this is how the overall model got typically created for us, right? So this is how we can look at it. Probably I can look at the summary of this particular model, fit underscore C3. I can look at a summary of this, which says it's simply a binary tree, so I don't need to talk too much about it. But if I'm talking about the structure of this fit underscore C3, I'll get a lot of things as a part of the structure. So whatever the things I want, I can very well access them by giving the dollars appropriately. So these are the different things that I can get through typing the structure. So I can very well take the name of the tree followed by a dollar and followed by the variable name. Right? So we are seeing where, we are seeing weights. So you could see different kinds of attributes that are coming as a part of this particular tree. The best thing is you can do a plotting of this particular tree. So this is how the tree came out. Wow. Smoker, right? Yes or no. The p-value is showing less than 0.05. Wherever the p-value is less than 0.05, that classification is a significant classification, whereas wherever the p-value is greater than 0.05, the classification is more and more insignificant, and there's no point in doing that kind of a classification. Now you could see all the classifications resulting in different number of nodes, and for each of the node there is a plotting of the data that has occurred. But because the number of leaves are very high in number, the graph is not looking that appropriate out here. So it's better that I can get into the process of pruning the tree, wherein I can set the tree controls where I can come out with the maximum depth of the tree as well. So we have estimated the model using the training data. We have got into the plotting of the model as well. So if required a few more information, I can very well do the printing. The most important things I need to understand are the branch number, the split rule, right? We have seen as a part of the print, or even if I type the name of the tree as it is, I could see a few important things. These are what are the split criteria: BMI less than or equal to 30. The criteria reflects the reported p-value. So here the p-value is much higher. So which is an indication that the classification is not a significant classification. But when I come down, right, here the criteria saying 1, which is mostly the 1 minus of the p-value kind of stuff. So the criteria showing a much higher number indicates that the classification is more and more appropriate. But if the criteria shows a very a lesser value, then it shows that then the classification is not appropriate, and there is no need to go ahead with the classification of that particular data using this attribute. Terminal nodes are always indicated with a star. So here we have 19 terminal nodes, here we have 14 of them, here we have 23, and so on. And weights are the number of subjects that are there at that particular node. So here there are 23 nodes, here there are 17 observations that are there at this particular node, and so on. Now, the next part for me is getting into the prediction part. So let me talk about pred underscore the fit underscore C3, where I am using the function called predict, right, where I am using fit underscore C3 as the name of the model. The new data for me in this case is the test data, and based on this there is a prediction that has typically occurred, right? The predicted values are there in front of me. Now either I can go into the plotting part, where I am taking the actuals. Actuals is coming out from the test data dollar charges, whereas the predicted is coming from pred underscore fit C3. So based on that, when I am trying to do a plot, I will get as kind of a scatter plot, which I could see that as the test data charges are increasing, even the predicted values are also increasing, which means there is a kind of a positive relationship between the two. for each of the branches. But the more appropriate way of trying to assess the goodness of fit of this particular model is going with the correlation between the two. So I can very well consider the correlation between these two variables and probably the r squared. Because I require the r squared, I'll take the square of these two things. So this case, it is telling me that the r squared is 87.65%, which is higher compared to the r squared that we have got in the earlier models. Right, when I've gone with the preliminary regression tree model, the r squared was only to the extent of 85.15%, whereas here I'm getting an r squared of 87.65% when I'm trying to test it out on the test data. So for this particular purpose, it looks like using a conditional inference based regression tree is more appropriate for predicting the insurance charges compared to the preliminary regression tree. Right, but again, we can very well look at a few other techniques which we are going to take up in this session: linear model based recursive partitioning and evolutionary regression tree, to see if there is any way we are able to improvise on the r squared. But you could see here different models are giving me different kinds of results. So the higher is the r squared that I am getting on the test data, I can very well go ahead using them for my assessment purpose. Probably if I am doing an AIC of the same, right, if I am going ahead with the AIC of this particular model, here I can't use the AICs and BICs, right? Even the log likelihood, I cannot use it for this kind of an object. So it's better that I go ahead with the r squared itself on the test data. See, whichever is the case where the r squared is higher, that model would be preferred for this kind of data for the prediction purposes. Alright, so with this as an input, now let's move on to the next topic, which is the linear model based recursive partitioning tree. Right? Now, going on to the next model, which is the linear model based recursive partitioning. So this is accomplished using the package party, and here we are using the mob function. So just like the way we have used the linear logistics, sorry. Just like the way we have used the logistic model based recursive partitioning for classification, we are using linear model based recursive partitioning for the regression tree. So if you remember, we have used a few parameters like this. The model was more like this. Z was like a continuous response variable. We have a few variables which are the covariates which are used for building the model, and we have a few variables ABC which are used for partitioning the model. So there are a few variables which are used for partitioning, and there are a few more variables that are used for building the model. So that is what we are doing as a part of the mob. Of course, the party package is already there with us, so I don't need to really specifically install it. I'm just it's already loaded also, because for the earlier model also we have worked from the party package itself. Now all these steps are already performed because we are working on the same data. So up to here things are fine. Now I'll go ahead in terms of estimating the model using the training data. So I'll call it as fit underscore linear underscore tree. Let me call it like this, right? Wherein I'm considering the mob function directly. I can use the mob. So here I have to define first of all f. In this case, f for me is, right, I will have to create it based on the dependent variable. The dependent variable in this case for me is the charges. Right, before that, let me actually look at the names. so that I can simply use them, some of them as a part of the model building and some of them I can use for partitioning purpose. So yes, the F, which is a model for me, I will look at it as charges being my dependent variable, and I will use age. Age is something I'll use for building the model. So sex I'll use it for bifurcation or partitioning purpose. BMI I'll use for building the model. The children also I'll use for building the model. Smoker I'll use for partitioning purpose. The region also I'll use for partitioning purpose. So these three I'll use for building the model. Whereas for partitioning the data I will use sex, which is the gender of the person. Then I would also use the smoker S versus no for partitioning purpose, and even the region where the person is lying, residing, even that we will use for the partitioning purpose. So this is the formula I want to implement. So based on this I can consider the fit underscore linear underscore tree, wherein I am using the mop function directly. The formula is F. The data that I am using in this case is the train data, right? I am using the train data for building the model. So earlier when we were using the logistic model based recursive partitioning, we have set the model as G linear model, whereas here I can set it as a linear model, right? In this case I will set it as a linear model. And if I want, I can very well go ahead setting some of the controls as well. But right now, without any of them, let me just do a plain fitting of the tree. So if I am looking at this particular tree, fit linear tree, this is how it has come out. So the breakdown has happened only on the smoker status, right? The other two variables like sex and region did not show any kind of an impact for partitioning the data. So for smoker status equal to no, where there are 739 observations, and this is the kind of a formula that has come out. So 262 times age minus 21.98 times BMI plus 647 times the number of children. So the focus is more on the number of children but very negative on BMI. Whereas when it has come to the smokers data, there is a very heavy impact of BMI on the model. Right, for every 1 unit excess of BMI, I could see that the insurance charges are going to be much higher out there. So that's the way we can evaluate the tree. And even when I'm looking at the plotting for this particular tree, the plot is very clear out here. Right, this plot is showing a much better kind of a picture. We are talking about three different variables out here as a part of our model. The first one is talking of with respect to age, right? I could see that for the smokers, so as the age is increasing, it looks like the charges are going up slightly with respect to the age, whereas in case of smokers, it's actually dulling altogether. I don't see age is playing any kind of an important factor out here. Probably you could see the way the red line is arranged, there is no pattern in the red line altogether. On this other side, when I look at it with respect to BMI, in case of non-smokers, again BMI is following a very randomistic kind of a pattern, whereas you could see in case of smokers, the BMI is showing a definite upward trend kind of a pattern. And probably the third one, which is the number of children, hardly making any kind of an impact in both the models. It looks more or less flat or probably up and down kind of stuff where the explanation is not coming out that properly. So this is how the model has come out for each of these variables. So I have already typed the model. and if required I can very well go ahead with the summary of the model also, which will give me the coefficient for each of the splits. So in case of the smoker, in case of non-smokers, the first group, so this is how the estimates are coming out. The BMI is really insignificant because the p-value is greater than 0.05, right? Whereas the other two, age and the number of children, are very much significant. So as the age is increasing, it looks like the charges are increasing. As number of children are increasing, even the insurance charges are also increasing. That is what is the model that is associated with the non-smokers, right? For every one extra year of age, in case of non-smoker, the charges are going up by 262 bucks, whereas for every extra child, it's going up by 647 bucks. Whereas when we look at it with respect to this model, right, we could clearly see that the age is 282. All three of them are significant here. No, sorry, children is not significant out here. The p-value is greater than 0.05. Age is significant, so for every 1 year of increase, probably the insurance charges are going up by 282 in case of smokers, whereas one additional unit of BMI is contributing to an additional charge of 1417 bucks. Now this is where the model is more and more complex. This is where the model is playing a much bigger role in terms of for the smokers compared to the non-smokers. So we are looking at the summary of the model, and that summary has given us this kind of a pattern altogether. Now I could very well use the log likelihood, right? In this case we can very well use the log likelihood model. The log likelihood of the fitment I can very well use. So when I am trying to compare with some other model, that model should have a higher log likelihood, and even I can very well introduce the AIC for doing the fitment. The AIC should be lower for that particular model, right? So I can very well go ahead with checking out all these things, which can help me to do the assessment more comfortably. Which model is better compared to the other? So let me just quickly rush through the stuff. So we have produced partial scatter plots. When I have used the plot function, we got partial scatter plots. One is with respect to age and the charges. We also got it with respect to BMI and charges, both for smokers as well as non-smokers separately. So our response variable against each of the regressors in the terminal node along with their fitted values. So the whole thing is typically being plotted. So when we are doing the fitting, we have seen that all these values are there as a part of the fitted model. I can very well use the summary to get more and more details, including the log likelihood of the model as well as the AIC of the model, so that I can, when I fit some other model to this particular data, I can very well assess the goodness of fit of these two models. I can very well do the comparison between the models quite comfortably. Now I can go ahead in terms of the prediction now, right? So I'll say prediction underscore fit underscore linear tree. I'll use the predict function just like the way we have been using till now. So this is the model that we are using, and the new data that we are using in this case is the test data. So we have got the predicted model. So either I can plot the graph of that predicted model, right? So I can very well plot the actual is nothing but test data dollar charges, and the predicted values are pred underscore fit underscore linear tree. So the plot is showing again there is some kind of an increase in the behavior itself. The probably there is a kind of a linear growth rate in the overall model, so it indicates that R squared could be quite comfortable. But just to be on the safer side, instead of doing the plot, if I take the correlation squared, which is what is my R squared for the comparison purposes, instead of plot, I will take it as the correlation squared, which is the R squared for the model. It says this is 85.71% only. So compared to the earlier model, again this R squared is lesser because in conditional inference regression tree model, we got an R squared of 87.65%, whereas in this case again it has come down to 85.71%, but slightly better than the preliminary regression tree model where it was 85.15%. But overall all these models are giving me some level of more or less similar layers of R squared for predicting the charges of the insurance. The insurance charges I can very well predict using one of these regression tree models. So, and the last of this set of models that I'm looking at here is the evolutionary regression tree, which we would be using on the same lines as evolutionary classification tree, where we have a package EV tree and the function is also an EV tree function. So I can very well load the package EV tree. Okay, the package EV tree is typically being loaded. The only information that I have to give here is Z is I'm not going into the help of each of these functions because we have already discussed these functions as a part of our classification tree. So the package and the functions that are being used as a part of the package, they are exactly the same whether we are using for classification purpose or the regression purpose. Only difference being the Z. The Z is a categorical variable in case of classification tree, and it is a numerical variable in case of a regression tree. So again, if you are saying the continuous response variable Z and data is the set of all the covariates. The process is exactly the same till this. So I can very well go ahead in terms of fitting the data directly. So I'll say fit underscore EV tree as the name of the model out here. So I will use EV tree, and in this case I have to give the formula. The formula for me, it's not a conditional stuff. So the formula for me is the charges tilde dot. That's the name of the formula. Data in this case I can very well use it as the train data. And based on this I can create the model. So the evolutionary tree model is being created and being fitted. Again, here also the depth of the tree can very well be controlled using evtree.control. I can set the depth of the tree, the maximum depth to be to 2 lines or 3 lines. The maximum depth to be at the 2 layers or 3 layers or even unlimited. Right? Probably if required. That's the original one. I can set fit underscore EV tree charges and the data, wherein I can very well use the control part. We will set the control. The control part I am setting it as evtree.control, wherein I can set the maximum depth. Right, so I can set the maximum depth of this particular tree to be, let's say, 2. Okay, so we are fitting 2 different kinds of trees here. Probably it's better that I try even with 3, all else remaining the same. The maximum depth of the tree I will set it to 3. Let's observe in all the 3 cases what is happening. So I'm fitting 3 trees out here. So the evolutionary trees, I'm fitting 3 of them, one with only 2 layers, one with 3 layers, and one with unlimited set of layers altogether. Right? So let's check out the tree structure for all the 3 cases. So when the structure is Q, right? So the root we are talking about smoker is yes and no. In case of smokers, yes, we got a BMI less than 30 and BMI greater than or equal to 30. 92 cases here, 106 cases here, right? That's the way the model got fitted. And in case of smoker being no, the variables that are being considered are age is less than 43 and age greater than or equal to 43. So this is how the model got fitted, the evolutionary tree with only 2 layers. But if I'm talking about an evolutionary tree with 3 layers, it's slightly more. Again, it's a smoker, but within the smokers, again, BMI is less than 30 and greater than or equal to 30. But within them, again, there is one more bifurcation that has come with respect to age less than 41 and greater than or equal to 41. And for BMI greater than or equal to 30, it is talking of age less than 43 and greater than or equal to 43. Whereas in case of non-smokers, the situation is completely different. Age less than 43 versus age greater than 43. And for the people whose age is less than 43, it's also checking for children less than 1, which means 0 child versus greater than or equal to 1. And in case of age greater than or equal to 43, it's again looked at with respect to age itself less than 52 versus greater than or equal to 52. So that's how this particular model has come up. And if I have completely ignored the number of layers, still it looks like the same. The 3 layered model only has come out. So I can very well ignore the 3 layered. I can say the unlimited kind of depth versus a depth of 2. I can look at both of them in terms of the summary, or even I can do the plotting for both of them. So I will look at the pit underscore EV tree for all of them without any control. So I could say smoker, yes, no, BMI, this. And for each of the nodes, we could clearly see that there is a box plot that is being plotted. For each of the leaf nodes, there is a box plot with respect with some kind of outliers that are being plotted as a part of the tree. The same logic probably if you are using EV tree 2, probably the plot is much more simpler. So we could see that the node tree talking about only 2 outliers out here. You could see that on a median scale, the charges are very much on the lower side. Whereas in node 4, where the BMI is greater than 30 for smokers, it looks like the charges are much higher. In case of non-smokers, it looks like the insurance charges are much lower. Based on the age of less than 43, they are much lower. For the age greater than or equal to 43, they are slightly on the higher side. So that's how we can assess the model. And even the summary I can very well compute. One with respect to nothing, which is the unlimited depth. When I am looking at the summary, yeah, there's nothing much that we are talking of. So summary we don't need to go ahead. In this case, just by typing it, I am getting the required information. Then I can go ahead in terms of doing the prediction. So I can very well say pred underscore fit underscore EV tree, wherein I am using the predict function. The model I am taking is pred underscore EV tree. The new data that I am considering for this purpose is the test data. Based on that, I am able to do a pred underscore fit underscore EV tree. I can also do a pred underscore fit underscore EV tree 2, where I would be taking the model also as fit underscore EV tree 2. So I can look at the plotting for both of them. The actual for me is test data dollar charges, and the variable that I am using, the predicted value that I am using is from the unlimited depth tree. Okay, so there is a missing out that is typically happening. Okay, so I have to put actually a comma, I have put a dot, so that's where the problem came out. Right, I can very well plot the predicted as well as the actuals. So looks like there is some level of an upward movement, right? But again, we really need to see what is the level of accuracy of this particular model. And similarly, when I'm going with this two-stage model, it is coming out more in this way. So rather than using the plot, I would like to see the correlation squared in case of unlimited depth tree. The correlation squared is coming out to 87.51%, the evolutionary tree. When we are using with unlimited depth, it has come out to 87.51, whereas when we are going ahead with the tree 2, it is around 85.15. So I could very well go ahead again using the 87.51%. It looks more or less similar to the here it is 87.65 in case of conditional inference regression tree, whereas here it is 87.51. So more or less these kind of trees are giving the R squared on the test data in a more or less similar range. So if we have to improvise on our model, we have to really look at any other parameters that are influencing the charges, and based on that we have to go ahead in terms of improvising the model. But this is what typically goes as a part of the entire understanding process. So let's quickly look at the steps. I hope we have already done with all these steps. We have fitted the typed the model name, got the details of the tree. We use the summary function to get more details. Right? We have used the valid observations, which is the test data, and the test data along with the fitted decision trees, both of them, the depth 2 versus depth unlimited. We have used both of them for the prediction purpose. We have looked at the scatter plot as well as the squared correlation coefficient between the predicted and the observed values. So in this case, there are a few more things that I can very well control. We can use the EV tree dot control. Here we have used actually the EV tree dot control. Only the maximum depth is something that we have used, set it to 2 and unlimited. But I can very well set number of iterations, right? In case the tree does not converge in the default number of iterations, it's better that I set the number of iterations for the process. Probably it would have been better if I had got an error that the tree is not converging, then I could have increased the number of iterations. And here we could clearly see that the decision tree models are typically outperforming, especially when the relationships are irregular. When the relationship between the variables are irregular, they are non-linear, probably I could see that the decision tree models are doing a much better job for doing the prediction of a numerical variable compared to a linear regression kind of model. So when the relationships can be very well approximated through simple models, in those cases it's better that I don't use the decision trees. But wherever the relationship between the variables are very complex, very irregular, then we talk about using the decision tree models, the regression tree kind of models for predicting even the numerical variables as well. So this is what I wanted to offer as a part of this session. We spent a good amount of time trying to understand the preliminary regression tree, conditional inference regression tree, the linear model based recursive partitioning, and evolutionary regression tree. With the same data, we have tried assessing which model is fitting well for this particular data. We have split the same data into same training data and same testing data. The models are fitted on the same training data for all the cases, and they are tested on the same testing data to maintain the consistency across the process. But again, let me tell you again with a word of caution there is not a single case which says this particular test is universally better than this particular method or algorithm on a particular data. So that's the reason we are trying all of them. We are using methods like AIC or log likelihood, or in this case we have looked at the R squared on the testing data to assess which model is much better compared to the rest of them. If you have any further queries regarding this, feel free to get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.